So with this monotonicity property of density connected sets, the algorithm for finding density-based cluster subspace clusters is pretty simple, pretty much the same as before with Clique. And the only thing is that we now plug in the dbScan cluster model and call it subclue. That's all. So here it is. The algorithm is very simple. As I said, we just look for all subspaces that contain any density connected set using a bottom-up approach, very similar to the Clique algorithm or to an a priori algorithm. Yeah. So instead of dense units, we now look for density connected sets. That's all. Yeah. And yeah, density connected clusters. Well, what we get actually is the same as in Clique. We get candidate clusters, density connected candidate clusters, and we have to make sure that they are still existing. So we're using a specialized dbScan run in the resulting subspaces to generate the final subspace clusters actually. Yeah? But at least with this a priori Clique style thing, we can explore the exponential number of subspaces like before. And like before, we have two input parameters specifying the density threshold, one for the volume, one for the minimum number of points in the volume. Now the volume is epsilon, the radius around each point, and min PDSS is the minimum number of points in a cluster as before. The output again is all clusters, the set of all clusters in all subspaces, and again clusters may overlap. So one point may be in different clusters in different subspaces. As before, in order to ensure this monotonicity criterion, we use a fixed density threshold for all subspaces. So we compare, for example, 50-dimensional subspace clusters and 2-dimensional subspace clusters, because we apply the same density threshold, the same epsilon, and the same min PDS to these subspaces. Yeah? The cluster model is now a little bit more advanced than these grid-based approaches, but on the other hand, it's also a little bit more costly. So we have to run dbScan or a specialized dbScan on the resulting cluster, which is a little bit more heavy than this connected component best first algorithm that we used for Clique, yeah, for finding these connected neighboring grid cells. But that's okay. Yeah, so the basic criticism of these algorithms, or say shortcomings of these algorithms, is that we have a fixed density threshold for all subspaces of any dimensions, and that we get a lot of redundant subspace clusters. Sometimes that is quite overwhelming actually. Yeah? So the question is, can we use different cluster models, maybe cluster models that rely on different density thresholds or whatever, yeah, some adaptive cluster models that are more flexible, more adaptive to the dimensionality of the subspaces we find those clusters in. And yes, there are a lot of variants, and most of these variants now use different bottom-up heuristics for subspace search, because in that case, or in those cases, the density, the monotonicity criterion is not fulfilled anymore for the cluster model, and then we cannot apply a priori or stuff like that. Yeah. So here is a variant which is called FIRES. It is also quite simple because it again starts bottom up with one-dimensional clusters called base clusters, yeah, and that can be now generated by any traditional clustering algorithm applied to each of the one-dimensional subspaces. Yeah. So we have one-dimensional subspaces, which are the simple features, and we apply any kind of clustering algorithm to those features individually, to those one-dimensional subspaces, and the resulting clusters are called base clusters. Now the question is, how can we merge those base clusters to form higher dimensional clusters? Yeah? And that is here by applying a clustering of the base clusters, yeah? Using a variant of dbScan in that case. And in that case, we define, well, we need to compare base clusters and see if they are dense enough or similar enough to be clusters, yeah, so to say. So we need a kind of similarity notion between clusters, and that is just defined by the intersection of these two clusters. Yeah, so if the two clusters have enough points in common, like CB here and CA here, they have these points in common, so they can be merged to higher dimensional clusters, so to say. Yeah, and the same holds true for CC and CA. Of course, it doesn't make sense to compare two base clusters from the same one-dimensional feature space, from the same one-dimensional subspace. So we won't compare CB and CC because they don't share, of course, any points. That's for sure. Yeah. So anyway, we start with these base clusters and then cluster them with the dbScan clustering algorithm. So we end up in clusters, and these clusters somehow indicate mergings, a merge of several base clusters, which are candidates for higher dimensional subspace clusters. And those candidates are refined using any traditional clustering algorithm, again only on those points here. So what we get actually, if we merge these two base clusters CB and CA, we get this, including this one here, of course, this approximation, which is a rectangular approximation, obviously, and then we apply another cluster criterion on that in order to find the final subspace cluster, which is this one here. So we would identify this one as not belonging to this. Yeah. For example. So you see that the heuristic now is, well, we still start bottom up with one-dimensional clusters, but the heuristic now is that we apply a clustering of these one-dimensional base clusters in order to merge them. Yeah? And the basic assumption behind all of those things here with these bottom-up approaches is that if we have a higher dimensional subspace cluster, we somehow see them in the one-dimensional projections. Yeah, like these clusters here, we see those clusters somehow in the one-dimensional projections. That is the basic assumption behind fires, behind subclue, behind clique, and all the other stuff. Yeah? And it's also the basic assumption behind the second variant. P3C it's called, which is also not branch and bound, because the cluster criterion is again not monotonic. The idea is very similar to fires. The cluster cores are hyperrectangular approximation of subspace clusters, the same as here. Yeah. And how do we get them? Well, the cluster cores are computed bottom up from so-called significant 1D intervals, and in this case we even can derive some monotonicity criterion for these significant 1D intervals, so we can use a priori style to compute them actually. Yeah? What means significant 1D intervals? Significant clusters, 1D clusters? Well, in that case the authors propose a hypothesis test. So the zero hypothesis is that there are no clusters, meaning that the points are randomly distributed. And if an interval contains significantly more points than expected, we reject these null hypotheses, meaning that we get significant one-dimensional clusters according to a given significance level. Yeah? So we just apply a different cluster model, which is an hypothesis test. The null hypothesis is that there are randomly distributed points. So as I said before, significant one-dimensional intervals follow the downward closure property, so we can use a priori in that case again. Different to fires in that case. Yeah? And the same as in fires, we get those rectangular approximations, higher dimensional rectangular approximations, meaning that we may have a large volume in these rectangular approximations, and that there may be some noise points like here. Yeah, so this one here is a noise point, but it is reported as part of this merging of these two clusters here. So we have to have again a post-processing like in fires, and in this case the post-processing just uses EM Gaussian mixture model clustering with the cluster cores as initialization. You know? So you see, you can throw any different heuristics on this problem and end up in getting something. Yeah, finally, I just want to show you very, very briefly that you can go beyond as far as you like. So here is a variant that finds subspace cluster hierarchies. Yeah, so we have this, of course, this information that lower dimensional clusters are embedded in higher dimensional ones. Yeah, so cluster hierarchies were typically in the traditional sense, in the non-high dimensional or non-subspace sense, the fact that we have a cluster nested or embedded in or more specific cluster nested in a less specific cluster, and we can do the same here, but now explore these hierarchies along dimensions. So we may have lower dimensional clusters embedded in higher dimensional clusters. Yeah, so for example here, a one-dimensional cluster embedded in two-dimensional clusters here, for example. Yeah? And maybe we want to reveal this one here. We don't go into details here, just that you know we can do that by integrating a proper distance function into hierarchical clustering. So, for example, into signaling or in optics. Yeah, and in that case, you can, for example, learn this proper distance function instance-based bottom up. Yeah, just that you know that you can do a lot of shitty or fancy or whatever things here. Short summary on this part here, subspace clustering. So we got to know several different variants, and there are many, many more. Most of them suffer from a key limitation, which is global density thresholds. Yeah, and that is just because in order to ensure the downward closure property, which again enables us to search for those density-based or whatever clusters, subspace clusters in a bottom-up, a priori-like way. Yeah, and the consequence of this fixed density threshold is that points in, for example, a 20-dimensional subspace need to be as dense as in a two-dimensional cluster or subspace, which, if we reconsider the cursive dimensionality, doesn't make too much sense here. Yeah? So that is rather optimistic assumption, because the data space, of course, grows exponentially with increasing dimensionality. So we have this problem, and the consequences are a strict threshold, as we said before, will most likely produce only lower dimensional clusters, and a loose threshold will most likely produce higher dimensional clusters, but also a huge amount of lower dimensional projections, redundant information, which is potentially meaningless, yeah, because we get all these lower dimensional projections of these higher dimensional clusters again. Yeah, because we look for them bottom up, and in order to get the higher dimensional clusters, we have to produce or generate the lower dimensional projections first in this bottom up search strategy. Yeah, so that was subspace clustering for this week, and that is actually what we where we also stop this week. So once again, keep your focus tonight on the Relegationsspiel, Holstein Kiel against 1. FC Köln. And then we'll see, hopefully, with Kiel in the first division next year. But next week we hopefully already know about it. So yeah, stay focused, stay healthy, of course. That is more important probably. And yeah, talk to you next week. See you.